Maybe can we just wait for a couple of...
Yeah, I can see that.
So a very good evening to everyone that's joining us today. Welcome to the 7th episode of the IRIS 2.0 webinar series, marking our inaugural session for this new year. Today, we delve into the fascinating realm of quantum computing with the Center of Excellence, Center for Quantum Information, Communication and Computing, aka CQuICC. This center is dedicated to pioneering research encompassing both theoretical and experimental fronts in the domains of secure quantum communication, quantum sensing, and metrology, as well as quantum information and computing. With a steadfast focus on quantum entanglement, error correction, machine learning, cryptography, and more, it is truly at the forefront of cutting-edge innovation. I would now like to introduce and welcome our panelists for the day. We have Professor Anil Prabhakar from the Department of Electrical Engineering at the Indian Institute of Technology, Madras. As principal investigator at CQuICC, his current research interests are in quantum technologies that have applications in metrology, quantum communication, and quantum computing. He is the co-founder of CQNew Labs and Quantfluence, both incubated by IITM, where the focus is on quantum communication and photonic quantum computing. Also joining us is Professor Arul Lakshminarayan, Professor and Chair at the Department of Physics at IITM. As the co-principal investigator at CQuICC, his research interests are in dynamical systems, especially Hamiltonian and quantum chaotic systems, quantum information, especially entanglement, many-body physics and thermalization, random matrix theory and its applications. Last but certainly not least, we are honored to have Professor Barry Sanders serving as our moderator for today's session. Professor Sanders is the director of the Institute for Quantum Science and Technology at University of Calgary and Distinguished Chair Professor, University of Science and Technology, China. His areas of research are implementations of quantum information, evolutionary algorithms, and swarm intelligence for quantum control and metrology, long-distance quantum key distribution, coherent quantum transport and protein complexes, nonlinear quantum optics, and algorithmic quantum simulation. I welcome all the panelists and the CQuICC team. Thank you for joining us today. Before we begin, I request everyone to please drop in your questions related to the topic being discussed in the Q&A box. Only questions from the Q&A box will be answered. Regarding questions related to your certificates, please visit the website that will be shared in the chat box shortly. Now, without further ado, let's get started. I now invite Professor Arul to please take over and start the session.
Thank you very much, Danya. A warm welcome to everyone. Let me get started by sharing my screen. Yeah, so as Danya said, this is a webinar of the Center of Excellence in Quantum Information, Communication and Computing here at IIT Madras. So we are a center with which has many faculty members, as we will see as we're going by, but we are also generously funded by Emphasis Foundation, which you can see a logo of below. So this is an interdisciplinary center with members from various departments. And just to give you an overview of the people and the topics which are there, the center has two main forks. One is on quantum information and computing, and the other is on quantum communication. And within quantum information and computing, we have quantum information theory, entanglement, which forms a very crucial part of quantum mechanics or quantum and its applications, simulations, many-body physics, quantum chaos, quantum error correction, fault-tolerant computing. And within quantum communication, devices and systems. And as I said, our members are coming from various departments. So you can see people here Is my cursor visible?
Yes, it is.
Yeah. So we have people like Pradeep Sarvepalli here from electrical engineering, Prabha Mandya, my colleague at physics, Vibha from physics, Sunetra physics, Rajesh Narayanan physics, Chaitanya from chemistry, Sanjeev from biotechnology, Rahul from metallurgy, there's Lakshmi Bala, Professor Balakrishnan, both physics, Rahul Marathi from management, Prabhu from mechanical engineering, Bijoy from electrical, uh, Nicola from physics, Prem from physics, Siddharth from physics, Krishna electrical, Nitin electrical, Deepa electrical, and our PI, Anil, is also from electrical engineering. So let me move on to, we are all very ably supported by a very large group, which is also growing set of students and postdoctoral fellows. So just to give you an overall idea of the kind of numbers which are involved in the center, we have 4 postdoctoral fellows at this point, 6 research fellows, senior, junior, 14 project officers, and so on. We're all very indebted to them for this. So getting into the subject matter, I thought I'll first devote a few slides to set out the story and then talk about the activities of the center, just presenting a sample of our work. Indeed, quantum mechanics is, this is actually from an article by Tegmark and Wheeler from 2001, Scientific American. I found this graphic to be very interesting, and I've stolen it from there. 100 years of quantum mysteries. In fact, the 100 years when this came, 2001, marked the 100 years of from Planck, from Max Planck. You can see here where the explanation of black body radiation started out with the famous, now what we call Planck constant, and the quantization of basically electromagnetic radiation. So that was a landmark paper, which then set out a series of events from Einstein's explanation of the photoelectric effect, the discovery of superconductivity in 1911, to Bohr's theory of atomic spectra. So this was really a big landmark event. And then the 20s, you can see the series of events here, and we are really poised at 100 years from now. You can see 1925, Pauli exclusion principle, 1926, Schrödinger equation, Copenhagen interpretation, and 24, in fact, Bose-Einstein condensation. So S.N. Bose, this year we are celebrating 100 years of Bose statistics. So even before quantum mechanics in its full-blown form, Bose developed a particular statistics which we know today half of the elementary particles follow. So this was a very remarkable discovery, which we are celebrating 100 years of this year. And next year, this is the major discoveries of Schrödinger's equation, Heisenberg, Dirac, etc. And in our story for the center, maybe, of course, all this is important, but also specifically Schrödinger's CAT paper, 1935, the Einstein-Podolsky-Rosen paper, or EPR paper, which set out a very vigorous set of arguments about the foundations of quantum mechanics. And then as you move on, of course, there's this great tragedy of the atomic bomb. But also it's very interesting how quantum mechanics, with all its, very mathematical and basic abstract foundations, is along the way, you can see it's sprinkled with major technological breakthroughs, from superconductivity, the transistor. I don't want to call the atomic bomb a technological breakthrough, but certainly it created a big bang. Quantum electrodynamics, and then as you move on, you can see that the theory of superconductivity came only much later. But again, concentrating on our center's work, Schrödinger's CAT paper, which highlighted entanglement, and Bell's theorem in the 60s, which took it from the realm of philosophy kind of to actual experiments. And in fact, the 1922 Nobel Prize was shared for essentially experiments which demonstrated Bell's non-locality, which illustrated the non-locality which is inherent in quantum mechanics and in nature. And also you can see the MRI scan from NMR experiments, nuclear magnetic resonance, and then you can go forward to the discovery of many particles. But you can see quantum information theory coming in here with quantum teleportation theory, which is one of the important things, statements from quantum information. So it's a very interesting story, and it's been a remarkable 100 years, and with many remarkable people developing these. But in fact, this is 1901, and since then, in the last couple of decades, even more has happened, significant developments in terms of experiments. And I think that's associated with this drive towards quantum communication and quantum computing. So here you can see a roadmap from IBM, which is developing quantum computers in terms of quantum bits, which are the basic elements of such quantum computers. And you can see how from 2019 it's going from all the way from 27 to more than 4,000 qubits in just a few years. So the practical applications of quantum mechanics are entering a definitively new era. Incidentally, in 2022, IIT Madras joined the IBM Quantum Network, and to access these developments of quantum computers. So let me, for those in the audience who are not very familiar with this, just give a really brief introduction to what I'm talking about. You can think of bits. We are familiar with classical bits. We say on and off states, say 0 and 1 is on and off. Then quantum states are corresponding states. You may think of an atom with 2 states, or as we will see, polarization states of light with 2 states, 0 and 1, let's say a ground state and an excited state of an atom. But quantum mechanics says that it's not only these 2 states, but all these superpositions of these states are accessible states. And in fact, the superposition is what gives rise to very non-classical phenomena, especially the fact that you cannot copy quantum states, like we can go to a copier and copy classical information. Quantum parallelism, which is at the heart of a lot of quantum algorithms. Secure communications, which is at the heart of quantum communications. All of these things rely heavily on quantum superposition of these states. And the other aspect of quantum mechanics, which form the, as we said, non-locality and the Einstein-Podolsky-Rosen EPR paradox and all of that, is entanglement, which happens when you have more than one bit of, so more than one atom, for example, or more than one photon, which is the basic unit of light, particle of light. So they can be entangled in a way which is very different from the classical one, and they can have correlations which are much beyond the classical. And these lead to what is popularly called as spooky action at a distance, but also led to this development of quantum teleportation and important aspects such as dense coding. And quantum mechanics is also inherently random. For example, if you measure superpositions like 0 plus 1, you could end up either in 0 or 1 and completely randomly. And in fact, this leads to these famous uncertainty principles, but also more practically today, there are quantum random number generators and to produce quote unquote genuine quantum random numbers. So to put it in a practical aspect, I've just introduced this slide to show you how just polarization of light, which you can see with a simple polarizer, is an example of that. So you can have polarization states of light which are vertical and horizontal, which are like the 0 and 1, which I talked about in the previous slide. But on the other hand, you can also have other polarizations of light like 145 and 135 degrees, which are these superpositions which I talked about. And that's just in a single photon polarization. But you could have nonlinear crystals such as this, pump it up with some laser, and the light which comes out can actually have two photons that are entangled with each other in this horizontal vertical plus vertical horizontal. So that's like the 0, 1 plus 1, 0. So you can produce entangled photons using these experiments. And in fact, our center uses the experimental aspects of this are heavily reliant on these kind of setups. So to come to the center itself, we have basic research, quantum information, quantum error correction, algorithm architecture, communication protocols, and applied research networks, quantum key distribution, machine learning, simulations, quantum chemistry. And we are deeply involved in the education aspect of this, as we will see, entrepreneurship, starting of companies such as Confluence and Q New Labs has already been mentioned, and outreach, conferences, schools, and workshops. The technology platforms, as I said, we are involved in photonics mostly, but we also access qubits on the cloud from IBM, which we have used, as well as other other sources of quantum computers which are available. So photonic quantum computing is on our radar. Quantum communication has already been implemented, quantum algorithms, machine learning, and so on. And also, diamond photonics is in our institute an important aspect which we are also involved in. So to give you a sample of the kind of work without going deep into this, I asked some of my colleagues to share their work, and they've given me this. This is from my chemistry colleague, Chaitanya, and his students, where they have used quantum computers to find the spectrum of these simple-looking molecules, but believe me that these are actually very difficult molecules to quantum mechanics. Although the equation was written long ago, we still cannot solve it in some way, and we were looking for more efficient ways to solve it, and quantum computers is one of those. So here, these are interesting molecules from also a point of view of applications like batteries, and using a combination of quantum computers and deep neural networks, these colleagues and students have done this work about simulations. As I said, quantum error correction is a very important aspect, and here my colleague from physics and electrical engineering, Prabha and Pradeep, shared with me this work, which is telling you, for example, this picture, as the number of qubits is growing, there is also an limiting error rate. So we need to, in order to get truly quantum behavior, which cannot be simulated on a classical computer, we need very large number of qubits and low error rates, and therefore error correction is an absolute necessity. Today we have more than 100 qubits, but noise is posing serious challenges. So our colleagues are studying how to have particular noise-adapted quantum error correction schemes, as well as topological codes. So, so you can look up some of these references, but this is a very important step towards practical realization. And my colleagues, Sunetra, Lakshmibala, and Balakrishnan, shared with me their work on tomograms, which is a way of finding these quantum states, especially to do with states of light and lasers and so on. How do we actually find what is the state? So this is a way of reconstructing these states, and those are called these tomograms, and they are useful in atomic, optical, and nuclear physics. So move on, and to show you just a variety of the kind of topics, here is a protein folding problem from my colleague from biotechnology. Sanjeev shared with me this, where As you know, proteins can come in so many different configurations, and that's a very large number of configurations, and that's where quantum computers it's hoped that they would be able to unravel some of these structures in a more efficient way because of the superposition, again, this parallelism, which I mentioned at the beginning of this. So they have also worked, and there is a paper which you can see which uses quantum computers to address the problem of protein folding. Just to give you a sample of recent publications, and there are many colleagues doing this. So we have random number generators, quantum machine learning, the tomographic approach to continuous variable systems, maximally entangled states of many particles, fault tolerance, quantum computing with fault-tolerant quantum computing, combinatorial designs, and more basic quantum information, the effects of chaos and their use actually in tomography, quantum key distribution protocols, deep neural network-assisted chemistry calculations, classical capacity of networks and codes and queues, studying how to queue erasure queue channels. So and here is the paper which I mentioned about protein folding problem using a quantum computer. And so on. So that's just really a small sample of what's been happening. So in the next few minutes, let me just tell you the activities of the center itself. We had several meetings. So here was an international conference from last year, January 23. We had a meeting where this was an international conference on progress in quantum science and technology, which had about 147 participants. There were 32 invited speakers, 8 contributed talks, and 45 posters. So this we will conduct at periodic intervals. This year, there was highly frustrated magnetism international conference with a very large number of participants. As you can see here, this is also a series of conferences, and our center was involved in its organization. And another conference which happened recently at Manipal Institute of Technology in Karnataka. We were part of that organization, as you can see, Quantum Technologies and Applications. And in fact, our center was involved in organizing a pre-conference event for a day there. And also there is the Tayur prizes, which have been given out for the last several years. Here is it's a set of challenges which are posed from 2020, and Sridhar Tayur from CMU has generously funded this. For example, we had last year a 25 by 25 grand challenge of using quantum computers or to have to write algorithms to if you had such a network of gates. So in terms of education, we are involved in this NPTEL program, and we have already run a cohort 1 where there are 90 participants. There are 30 college students, 6 faculty members, and 54 industry participants in this. And my colleagues have been involved, such as Professor Prabha here. And presently, the cohort 2 is going on. For those of you from the audience who is interested in such programs, you can check out the NPTEL website, and you can see how these programs are being run. And this is in the future. We are just having in a few days a workshop on quantum information and quantum communication, which is part of the National Conference on Communication 2024. It has a session on quantum computing and information. And the international series, which is the 16th edition of quantum communication measurement and computing, is going to happen here in IIT Madras, being organized by colleagues from my center here, from the center here. So this is going to happen in August of 24. So the last one happened in 2022 in Lisbon, Portugal. The center has been in the media for various aspects. So here, this was an news item from 22 when IIT Madras joined the IBM Quantum Network. And the collaboration with IBM continues. Sorry. So this was a problem, in fact, which was solved by members of the group, including a PhD student of mine. So this was an open quantum information problem related to many particle entanglement, which kind of solved a very old problem of Euler's, but from a quantum perspective. So this got some attention. We have this magazine Shastra, which covered, in fact, Professor Barry Sanders, who very kindly agreed to be our moderator today, was also interviewed extensively in this article. And so also the work of my colleague, Chaitanya, whose work on chemistry I mentioned, was also covered about lithium, sulfur, and lithium-ion batteries. In this. And then the 3-day conference, which I mentioned about in Manipal, was also covered in the press. So I think I've taken more time than I probably should have. So thank you for your attention.
Thanks, Arun. I guess this is my cue to continue. Let me share my screen. Okay. I'm assuming that my screen is now visible.
It is.
Okay. So I'm going to pick up from a very specific topic that Arun spoke about in terms of cryptography. And I'm going to take you down a journey of some implementations that we do. I would request my colleagues on the panel to keep an eye out on the question and answers. And if they can answer some of the questions there, that would also be helpful. So the title that I've chosen is Quantum Key Distribution from Makan to Kida. And hopefully before the end of this short presentation, you will remember these acronyms Makan and Kila, because you're bound to keep hearing more of them in the coming months. The outline is very simple. We are rethinking our public key infrastructure with a focus on quantum key distribution. And it's dovetailing into the National Quantum Mission that has been announced. And we are hoping that to play a large role in that. A lot of this work is collaborative along with other research laboratories and industry. So very quickly, if we talk of our infrastructure at the backbone, what most of us do not recognize is that there is a large fiber infrastructure, optical fibers, and they form different kinds of rings. We have the metro and the access area networks that connect businesses and lands. And then you have the long haul networks at the backbone that connect different cities. And all of this is running on optical fibers. And this information that is running on these optical fibers runs at different data rates. You can see that In the access networks, you may be at a few gigabits per second. In metro areas, you'll go up to about 10 gigabits per second. And by the time you reach the long haul, you're running at 40 gigabits per second. There is also this idea of wavelength when we do optical communications, and that is determined by this loss in optical fibers. On the y-axis is attenuation in decibels per kilometer, so it's a logarithmic scale. And you'll see that the minimum is around what we call the C band, or 1550 nanometers. And at this particular point, we have the lowest loss, which is about 0.2 decibels per kilometer, which translates into an interesting number, which is 1 in 100 photons reach the receiver, right, over 100 kilometers. So you'll understand the limitation of running quantum information or running classical information on quantum particles down these fibers. So what is the reason for us to pick up this idea of quantum key distribution? It comes from the very simple notion of security of our communications. Here is a cartoon that says that, you have two parties, Alice and Bob, and they share a public key and a secret key. And the public key is used to encrypt, while Bob, who has a secret key, will decrypt it. And this is our current infrastructure that we are using today when we use the internet for our banking or booking tickets or movies or whatever else we may do. Usually there is an eavesdropper who could be malicious or not. So that's usually a Mallory if they're malicious, and Eve if they're just a passive eavesdropper. And the idea is that we want to be able to safeguard our information from such an eavesdropper. Today's classical key distribution relies on computational complexity. So as an example, there is what we call the Diffie-Hellman protocol, which assumes the complexity of a discrete log problem. Right? Now, a protocol that relies on computational complexity also means that we are assuming that there is no hacker out there who has a computer that is strong enough. And that is where the danger is, because we are aware today that with AI, ML, and quantum computing, there is a very finite chance that a lot of our passwords are easily broken. Then, of course, we do have our traditional ways of distributing keys, and this always amuses me because the photograph on the left, of course, I got off the internet, but the one on the right was something I had clicked when I was taking a train journey. And you cannot actually see it, but the little label that is there on the second box said key distribution. And I was just very amused that we would put up labels that say key distribution on our black steel boxes and send them through second-class train compartments with security guards. And surely we think that we can do better than this. Right? Arul had shown you this particular picture, and I'd just like to draw your attention back to it to point out that with the number of qubits that are coming online, and this year in 2024, IBM's roadmap says we'll have access to 1,000 qubits. And there are other technologies also coming online which are accessible. You are now reaching a point where you will not know when your public key infrastructure is insecure. So if someone is actually able to crack your password somewhere inside this red zone, they have enough compute capabilities inside this red zone to crack your password, they're not really going to tell you this. There is also a protocol called the SSH that is used, which requires us to change the key after every 10 to the power 9 bits. And if you remember the earlier slide where I said that we are using gigabits per second, this is 1 gigabit of data. So every second you're supposed to change your key at the back end. And how can you do that if there is so much compute power that can hack your passwords? So if you look at this current security assessment that uses artificial intelligence, it says that the time it takes a hacker to brute force your password in 2023, and let's say you have 12 characters, the mix of upper, low, and lowercase is 226 years. However, if you just do 8 characters or 10 characters, it's within minutes to hours to weeks for the strongest password to be broken. And that is 2023. You can imagine that this thing is going to keep changing, and this red region is going to come lower and lower so that people can actually hack your passwords quite easily. So this is a real and present threat. Another threat that we have is when we actually look at our optical networks, you will find images like this, right? What is supposed to look like on the top right, which is a very nice, clean splice box, might actually look like something on the bottom after you have gone through a series of floods. And if you break open the splice box, you might even see light leaking out. What this is actually a way for hackers to hack into, or eavesdroppers to eavesdrop on your communications. So not only do we have to guard against things like this, we also have to encrypt our communications. I'll give you another very scary picture where if you send information on one of these fibers, which is on the right, and you put today's best detectors, which are single photon detectors, on the left, I can actually pick up a signal that is being sent on the right fiber without it being in contact with the data carrying fiber. So you can see out here that we are having information leak from one fiber to the other fiber in real time. So it is very real that someone can hack into our communication channel. So what do we do about this? We rely on the properties of light, right? And this is a very simple tutorial on the properties. There are three different properties. Arul mentioned the one about polarization. You see the picture out here where the electric field is polarized vertically. We also have color, which we are all very familiar with. If you think of a rainbow or a glass prism, it splits white light into its different spectrum. And then the last property that we usually use in communication is this idea of phase. And you can see two waves out here that are out of phase by a certain shift in time, right? Now, we are going to focus today on this idea of phase. And to understand phase, I've put up two simple pictures out here. This is the one about diffraction. And you'll see how light, when it diffracts off a slit, forms a maxima, and then it has certain minima. It also has null points where there is what we call destructive interference. And if you set up an experiment carefully, you can actually get diffraction out here, a diffraction pattern, which is very nice. And if you think of this pattern in 2 dimensions, you will see rings. Diffraction rings are very common. In fact, we see them very often during an eclipse. Unfortunately, I forgot to put that photograph, but that's a very nice photograph also. When we come to quantum mechanics, we rely on something called wave-particle duality, where each particle acts as a wave. And this is something that we discovered early on during the first quantization. And then we also understood that each particle interferes with itself, which is non-intuitive. How do we decide that? It's because we have certain null regions where there is complete destructive interference, and that's a very wave phenomenon. So when you throw, if you were to throw tennis balls through windows, you would not see this accumulation at particular locations. However, if you were to use quantum particles through a double slit experiment, you would see that they would accumulate at particular locations, and there would be dead zones in the middle where there is destructive interference. So this idea of a particle acting as a wave can also be taken back and said that waves can act as particles, and that actually is what we are doing with quantum communications. This is a picture to explain how phase is used in our classical communications. It's a very simple idea that you have a series of ones and zeros, which you then want to encode on this green wave pattern. And everywhere there's a transition, you'll see a change in the phase. And that phase is a change of pi. And so this particular pattern is what we call differential phase shift keying, where the difference between 0 and 1 is a transition, and that is where we are actually putting in our phase difference, right? This is done classically, but can you also do it with what we call a weak coherent state or a single photon? And the answer is yes. And the first demonstrations for this were as early as 2004 by the Japanese, and his group, where they showed that you could use a phase modulator with a weak coherent source and add the phase between successive pulses. And then how do you recover that information? You send it through this structure, which consists of 2 beam splitters and 2 detectors. And if the phase difference was 0, then it would come out on detector 2. If the phase difference was pi, it would come out on detector 1. And that's a very simple construct. This similar construct is also done in our labs. And you can see out here that if I have a long optical pulse, which is the red pulse, and I put a shorter phase pulse, then the first half of the optical pulse has a 0 phase and the second half of it has a pi phase. Similarly, I have a pi phase or a pi 0 phase or a 0 phase. So just by delaying the dotted blue line, which marks the phase with respect to the optical pulse, we are actually able to do phase shift key. This is where the security actually comes in for us. We are able to take this phase information and send it down the fiber to Bob, who then recovers it based on the clicking of the detector. So it's either D1 or D2, depending on whether Alice had put in a 0 or a pi. The security proofs for this actually rely on spatial superposition, where people break up the photon into 3 different parts. But you can also show that it is much easier to implement if you do it in the bottom picture, and that is what we do in our labs. But this is the science. What about the engineering? It turns out, of course, that there's a lot of engineering that has to happen before you can build a system. And there's a lot of classical communication and classical techniques from information theory that do authentication, key shifting, error correction, and privacy amplification before you reach the encryptor. So while the quantum channel keeps a raw key at about 100 kilobits per second, the encryptors are then encrypting your data at 100 gigabits per second. Remember that every 1 gigabit of data you need to change the password, right? So you do need a certain ratio between the raw key exchange and the actual classical encrypted data. So our boxes look like standard boxes on a network. They are 19-inch rack mountable. They have modulators inside them. They have the electronics chips inside them. They have single photon detectors. But overall, they should all fit into these rack mountable systems. So that we are then down to doing field trials on what we call MACAN, the Metro Area Quantum Access Network. This is a picture from our live demonstrations between IIT Madras Research Park, and the Society for Electronic Transaction Security in Chennai. This network was the first demonstration of a star CQuICC network in India, and it also required that we do a picosecond synchronized clock distribution over optical fiber, and we have also used what we call wavelength division multiplex classical and quantum channels. In our the field trials are not yet over. We are still expanding it. We have onboarded Bharat Electronics onto it. We're onboarding EarNet onto it, and then we are extending our links all the way to a location about 15 kilometers from our campus as a test bed. So this test bed is useful in trying out different types of quantum communication, not just quantum key distribution, but also secret sharing, queues, and setting up some standards for quantum networks. The standards for quantum networks are important because finally, at the end of the day, we do need to have a network that is secure, that is at the bottom of this picture, and a user network at the top that is able to use our keys. And we manage this network using a software interface that was built by CDAC Trivandrum called Darpan Q, and it allows us to see which links are active and which links are not. So where is this all leading us? It leads us towards this National Quantum Mission. The National Quantum Mission has set us goals of intercity quantum key distribution over 2,000 kilometers with trusted nodes using wavelength division multiplexing on existing optical fiber. It has a multi-node quantum network with quantum memories, and it requires low-loss fibers, and we require some post-quantum cryptography. We don't have the time to talk too much about post-quantum cryptography, but we do have colleagues who are very strong in this area, who are helping us build more secure networks. The picture on the right is important because it shows you that without having quantum repeaters, you're limited to about a few hundred kilometers. And as you start increasing your distance, the rate at which you're able to set up your passwords keeps decreasing. you do need the quantum repeaters, and there is a lot of early work, research work going on in trying to build something like this. The National Quantum Mission, we are hoping, will also allow us to connect Chennai and Bangalore. This is our proposed link with about 550 kilometers of fiber, with stations every 30 to 50 kilometers from BSNL. And we have also built photonic integrated circuits that we are expecting will be with us in a couple of months, that we can then deploy and test. Once that is done, the National Quantum Mission will then hopefully allow us to do the quantum internet with local access, which is got the acronym KILA, and that will connect Bangalore to Delhi through the cities of Hyderabad, Indore, and then finally Delhi. And at each of these locations, we are hoping to deploy more of these metro area quantum access networks. As you can see, these challenges are very large. They are national challenges, and we are hoping that our center will be able to play an active role in deploying some of these technologies. The quantum communication team has some faculty, Prabha, Krishna, Nitin, and a lot of students, many of whom have graduated and whose photographs are not out here. But we are looking at both the metro area quantum access networks and the quantum internet with local access, and working on standards. Neither Arul or I have had time today to talk to you about the hardware we built. We've got photonic quantum computing, photonic annealers, and sources and detectors. So it's a lot of experimental work that happens at our center. And this happens in collaboration with colleagues from physics, electrical engineering, and other research labs also. I'll finally end with acknowledging our funding agencies. You'll see that we have got a lot of funding from many different departments. And although our work started quite early in 2005, it's really picked up in the recent years with the current focus of the National Quantum Mission. Thank you very much for your attention.
So will Professor Barry be saying a few words?
Yeah, thank you. Thank you. So I'm really enjoying this session. I just wanted to just summarize some key points from both speakers. So from Arul, we had an excellent summary of the history of quantum mechanics, quantum science from around the early 1900s, actually, from the year 1900, which was really helpful for all of us to get a good context on what quantum science is all about. He also talked about the activities and the successes of the IIT Madras Center, which is doing really formidable work and has an excellent team. The emphasis connection is really important. There's the industrial link, and I'll just mention I'm at the University of Calgary, and we also have an emphasis link here. So we have the pleasure of sharing close collaboration with a particular company. The Shastra article highlights and explains a lot of what's going on with ITM and the quantum activities, and the international conference was key in establishing the momentum. And then Anil talked about quantum technology. So the bridge was from the quantum science to the quantum technology and quantum engineering, with particular emphasis on quantum key distribution. Quantum key distribution is vital to protecting India and the world against quantum computer attacks, and the fit within the national quantum strategy and the way to build up transnational links was provided. And then I just wanted to mention here, just to give everybody a broad context, that the way that we think about quantum technology now, there was the 20th century quantum technology that was embedded in Arul's talk. Things like transistors, lasers, magnetic resonance imaging. These are examples of successful quantum technologies, also superconductivity. And then now in the 21st century, we feel that there's a new level of technology brought about involving things like entanglement that you heard quite a lot about. The idea is that instead of just quantum saying it's the size of an atom or it's a molecule, a single object, but the idea of having multiple objects that share entanglement or some other quantum resource is key. And then the application areas that we focus on are sensing, so how we can use quantum technology to be able to sense past the intrinsic noise that's inherent if we don't make optimal use of quantum resources. Quantum communication, of which the quantum key distribution was part, and teleportation was also mentioned. That's another example of quantum communication. And then quantum computing, which was a key point and certainly a focus of emphasis that was mentioned in these talks. And quantum computing is really about a radical transformation to how computing is done. It's not about making computation faster for everything. Sometimes there's this notion that quantum computation is about speeding up computation. It's not. It's about certain problems that are considered to be hard to solve can become easy. And one of the examples is factorization of numbers. And that's what the threat is to security of communication. And that's why quantum key distribution is important. So those are just some comments I wanted to make, enjoying the talks, summarizing what was said, painting the picture, the kind of the big picture of where quantum technology is going. And then it's a pleasure for me to be in this session as IITM is a leader in breaking through some of the tough problems between us now and using quantum technology in the future. So those are my comments. Thanks.
Thanks, Barry.
Thank you.
That's very helpful. Danya,
So,
should we take a few questions?
yes, please, Professor.
Are they able to speak, or do we read it out from the Q&A?
So we can pick out a couple of questions from the Q&A box.
Okay. All right. So Nikhil asks whether there are any thoughts on quantum communication using satellites. And the answer is very much yes. There are many worldwide efforts to do quantum communications through satellites. The focus today was the work we do on terrestrial quantum communications. There are other groups in India who are looking at satellite quantum key distribution. And the challenge out there, of course, is to be able to find base stations where they have good visibility, and you can get these single photons to reach the base stations. There is an issue out there. Okay, here's a question on post-quantum cryptography-based homomorphic encryption. Is it really feasible to secure information from real-time quantum computing attacks? Barry, do you want to answer that?
Sure, I'll comment. So quantum key distribution is one approach to being able to secure against quantum computational attacks, but not the only one. The key point of quantum key distribution is it's intended to be information theoretically secure, which means it's invulnerable against any computational attack ever. But currently, the way that we secure communication is not information theoretic security, but rather computational security. So when you're using, say, a secure shell to be able to communicate, you're using algorithms to protect based on the belief that cracking the code is just hard, but not impossible. And so post-quantum crypto is an extension of that idea. So it says, okay, let's take the current idea of security, and instead of trying to make it completely invulnerable to quantum computers, let's just make it hard. So there's a huge effort going on, particularly in the United States. The National Institutes for Standards and Technology has a competition going on to develop a post-quantum crypto standard soon. And then the idea is that it can use a classical, i.e. non-quantum infrastructure to be able to encrypt and decrypt and send. And so post-quantum crypto is an approach that allows us to defend against quantum computer attacks in a computationally secure way. And longer term, quantum key distribution gives us an approach to protecting with a quantum infrastructure information theoretically, so invulnerable to quantum computers or any future science fiction-like computer that might come along. So the answer is really quantum key distribution is one piece of trying to defend against quantum computer attacks in the near, medium, and long term.
Thanks, Barry. Sanjeev, there's a question asking about possible uses of quantum computing in the healthcare industry. Would you like to comment on that?
Did you want me to comment or somebody
No,
else?
I've asked my colleague,
Sanjeev.
Professor Sanjeev.
Biotechnology. Yeah.
Sanjeev, we can't hear you.
Yeah, we can't hear Sanjeev.
All right, Arul, you want to take that?
Not really. I think you are probably more experienced. I think you should. You've been writing stuff on it.
Yeah. Well, in the healthcare industry, there are a couple of problems that we work on. Of course, there is the one that Sanjeev himself works on, which is protein folding. And from the one slide that Arul had, you'll see that predicting disease caused by the incorrect folding of proteins is a very large problem and a difficult problem that many people worldwide trying to tackle. And the quantum computing is one approach that we are hoping will help us answer some of the long-standing questions in that area. There are other simpler, lower-hanging fruit that try to improve on current machine learning techniques through an area called quantum machine learning, where we try to do image classification. So, for example, you can do binary image classification on images of lungs and try to classify them as having tumors or not having tumors. So quantum machine learning is one way that people have started using it, but I think the real benefits of quantum computing will come if we can simulate quantum mechanics of interactions, either proteins or drug molecules, and that I think is a big area for the medical industry.
So Anil, I would also like to, can you hear me?
Yes, please go ahead.
Yeah. So I would also like to add that, something as fundamental as the, biological process like photosynthesis,
Right.
it's suggested that it has quantum origins. So the connection between quantum mechanics and life or life processes, I mean, that's just, that's totally unexplored, and we don't even know what lies in the future. So I think quantum biology or, something quantum origins of life or photosynthesis or more development in that's going to be a very hot area.
Yeah. There is one more that I remember, it's not directly the healthcare industry, but it could be, the greenhouse gases. So we have students who are now simulating the interactions of the CO2 NH3 complex and trying to understand them on a quantum computer. And that's one of those greenhouse gases that we are interested in. So I think the benefits that could accrue from successfully solving some of these problems at a fundamental level would be quite amazing.
I guess you can hear me now.
Yes, now I can. Yes.
Yes, my Mac went to the iPhone. Yes, so yes, Anil and Arul Vaibhav added important points. So my say is that those are very long term, but at the moment, with available resources and the technology which are coming up very quick, with that couple of problems which we can easily solve. One is drug screening. So drug screening is going good in classical machines, but now as the number of molecules being deposited in database is growing exponentially, so here here quantum computing can play a very pivotal role to screen the molecules in seconds. Because drug repurposing, as you have seen during the corona time, drug repurposing can be a game changer, and here quantum computing can play a very important role to get you one of the existing molecules to help in some of the diseases. That is one. Another problem which I foresee would be very, quantum computing can help very quickly is getting the entire genome, be the human genome or the viral RNA sequence. So, scientists are able to get small fragments of base sequences, but then putting them in the right order is a big question, and it is still expensive to get the whole genome sequences. So here, quantum computing can basically assemble, disassemble, and get the optimal sequence pretty quickly. So to me, these two are pretty, we can foresee coming up in the coming few years, at the most to the decade. And other solutions or other problems what Anil and others said, those are also quite feasible in long term. Thanks, Anil. I'm done.
All right. Do we have any comments on solid state NMR for quantum computing? Request one of our panel members. Prabha, do you want to say something?
Siddharth, maybe?
Siddharth, is he on?
Yeah.
Yeah. Okay. Siddharth?
Actually, I should, maybe when Siddharth is saying, at the moment, it's just liquid or NMR, which is being used mainly not. I mean, it's a question of about 10 to 20 qubits, so to speak. So it's still at a early stage, and the scaling is considered to be an issue there. I'm not an experimentalist, so that's my limited understanding of this. Solid state NMR, I don't think this has been really pressed into at this point.
Yeah, I think we'd probably do more in terms of quantum sensing with the NMR aspect.
Yeah.
Build better sensors, better MRIs, and so on. I'll very quickly address a couple of questions that are there in terms of when quantum computers will be available to the public and whether they can help with IoT devices. I think quantum computers will always be like supercomputers in the near term. They will be accessible to the public on the cloud through some payment gateways. And they are already there. You can sign up to it through Amazon or Microsoft Azure Q. But I'm not entirely sure how they will help directly with IoT devices. You might find that you can solve problems in optimization on where do you place IoT devices, how frequently you service them. Those kind of problems that would fall under the NP-hard problems could benefit from having quantum computers. Still early days, we are not sure whether there is a definite benefit, but we are seeing some possibilities that is the case. Danya, it is past the hour. I'm not sure if we should be taking more Q&A.
So what I can do is send you a report of all the questions that were asked today, and maybe if you can give us the answers, we'll put it up on our website.
Sure. We could definitely do that.
So we also had a couple of questions relating collaborations and how do we get internships at your center. So maybe if you could say a couple of words about that.
Yeah, I've been trying to type answers as quickly as I can while I've been speaking. So I just for the all the students in the audience, we do have the IIT Madras Summer Fellowship. The programs are open right now. If you're an undergraduate student, if you're a graduate student, usually the internships will be taken through the specific faculty. So you have to identify your area of research and reach out to faculty at the center to understand how you can engage. We do also not just students, but also we do host many faculty from other institutions through various schemes. So please do write to us and we'll be happy to point you in the right direction. And I think there was a couple of questions on collaborations from startups. We are obviously very open to collaborating with anybody. I will re-emphasize this as I do in every fora that we are at the starting point of a very long journey called the National Quantum Mission. It's a very collaborative effort and we do need to join hands in order to be successful in the mission. So please do reach out to us and we'll be happy to find ways to collaborate.
Thank you so much, Professor Anil. Thank you so much, Professor Arul and Professor Barry. Thank you for doing this, and everyone who stayed back with us at this late or early hour, depending upon where you are. Thank you so much. We will be updating the recording of the session on YouTube. Please do follow the links that I've put in the chat box. So, and you can also get in touch with us. And we will put you in touch with Professor Anil or others from the CQuiCC team. So thank you. So yeah, good night.
Thank you very much. Good night,
Thank you,
everybody.
and, thank
Thanks,
you,
Barry.
thank you very much, Barry, for joining us, and yeah, and thanks to all my colleagues who have answered 39 questions, and all those people for asking questions. They're very interesting.
Well, we have to apologize for the ones that we could not answer. Some of them were very hard.
Yeah, about entanglement leading to instantaneous communication across the universe. No, unfortunately. So, but it's a very interesting question. Thanks a lot.
All right. Good night, everyone.
Good night.
Maybe we'll end the meeting.
Sure.
Okay. Thank you.
Okay, bye.
Bye.
Good night.
Good night.